9.3 is going to be the shortest section so far. How cool is that? I see big eyes because that thing means we might actually finish it and you might end up with 2 homework assignments, I think is what might happen. We'll see. We'll see how far we get. I want to talk to you about a couple of different types of tests. I should start here. The integral test and the pSeries test. Okay? So integration, something we all know and love. Well, at least we all know it anyway. So a reminder to you about something we encountered earlier on. Generally speaking, we need to be able to test for convergence without finding the sum. Because sometimes it's not even possible to find a sum, okay? So if we just go looking for sums, then we can't even find it, then we're kind of stuck with, well, did it converge or diverge? Well, I don't know because I could never figure out if I could find the sum, right? This is sort of a circular thinking problem. So in this section, we're going to start looking on how to do that. Okay, how can we find converge or diverge, even though maybe we can't find what it converges to, if it really converges? And one of the tests that allows us that kind of insight is theorem 910, called the integral test. And it says the following: if f is positive, continuous, and decreasing, for the values x greater than or equal to 1, and a sub n, our sequence, is equal to the value of the function of that at n, then the summation from n equal 1 to infinity of a sub n and the integral from 1 to infinity of f of x either both converge or both diverge. Notice what it doesn't say. It doesn't say they're equal to each other. Right? It does not say they're equal. It just says that convergence of one means convergence of the other one. Divergence of one means divergence of the other one. And this is not the types of integration that you did that many of, right? There's an infinity as the upper limit of this integration. It's called improper integration, and you did it, but you probably didn't spend a whole lot of time doing it, so you might need a refresher about how you examine that particular part of this. And we're going to do that with an example. Surprise, I know, right? Examples, say what? All right. So we're going to confirm the integral test can be applied. And then we're going to use it to test for convergence. let's give it a shot. Here's an example for us. We're going to start at k equal 2 to infinity of 2 over k ln k. And we want to know, does it converge or diverge? So the first thing that we have to do, if you look back at the integral test, is it talks about looking at the function itself and deciding if it is positive, continuous, and decreasing. And we have to confirm that it actually fits those criteria in order to start. Now, we're not interested in like a full-out proof here. That's not the point. The point is to make sure it can really be used, okay? So how does that look? Well, for the sake of what we're doing here, we're going to have to create the function. I'll call it f of x. And it will look like 2 over x ln x. I think we can confirm the positive part pretty quickly because logs are always positive after a certain point, right? A log graph, if you're just thinking about the log part of this only, looks something like this, yes? And after some point, somewhere, this is my point on my graph, it's always positive values, okay? We'll deal with the other two parts later, but can you see that if I plugged in, this is starting at 2, right? A value of 2, the natural log of 2 is positive. Times the 2 in the denominator, that's positive. And anything bigger than that's going to work. So the positive part you almost get for free, all right? It is positive. Okay, so we're going to try to check it off as we go. It's positive. What else did it say we had to confirm? It's continuous. Is this graph, is this function continuous? It is continuous. There's no vertical asymptotes. The only vertical asymptote would exist if natural log was equal to 0, okay, which it never is, right? And or if x is equal to 0. And it isn't either in this area, right? I'm referencing my k to 2 to infinity part, not the ever part, but in the 2 to infinity part. Yeah, so it's continuous. So I'm not going to have any vertical asymptotes occurring because I've got zeros in the denominator. And the last piece talks about it being decreasing. Now, I mentioned this fact that the log itself is an increasing function, right? Yeah, it is. And x is also an increasing function. So the denominator increases. Bigger numbers, bigger denominator. So what happens if your denominator of a fraction gets bigger while your numerator stays constant? It's decreasing. Okay, so this is definitely decreasing. So we've kind of talked through it. And you can do that. That's great. If you were asked to justify it in a little bit more formal way, you could just use that description, and I'm good with that. Another thing you could do is grab your calculators, and we'll do this real quick. Grab your calculator and just graph 2 over, parentheses, x ln x. And you can visually confirm that after x equals 2, that it's positive, that it's continuous, and that it's decreasing. I've got Kristen nodding her head. She's got it in there. Chris, are you good? Yep. Okay, I'm practicing names. Kyle, right? Kyle's nodding. Okay. Did everybody get their calculator to agree that Ethan's good? Awesome. Okay, so it fits the description needed, which means I can use the integral test, okay? So as we use the integral test, now what? Well, we change it into an integral that we're finding. So we're going to consider the integral from 2 to infinity of 2 over k, we'll use x's just because it's a little more comfortable, x ln x dx. Okay? How do you use integration for this? What do you do? Nope. There's no quotient rule, unfortunately. Derivatives have a quotient rule, but not antiderivatives. It's okay. It is u substitution. Good eye, Shayna. So the u value is actually our log, ln x. What is du? That is, what is the derivative of u? 1 over x. Do you see that in your problem? Yeah. So this can actually be written as, I'll leave the 2 and the infinity off for a moment so we can talk about them, but as 1 over u du. This x and this understood 1 above it, and the dx all get replaced with the du. I didn't mean my 2 to become a 1. There's a 2 still in the numerator. 2. 2 over u to u. Are we good with that? Yeah? Okay. So now let's see what happens. What is the antiderivative of 2 over u? It's not a straight question. Huh? Yes, it is 2 ln of u. And I didn't really start with u's in the problem. I started with x's in my problem. How are u and x related?
U and x ln x.
U is ln of x, right? So this is the natural log of the natural log of x. And we're trying to evaluate it from infinity, quote unquote, down to 2. So while conceptually we understand the idea of plugging in infinity, that's not very mathematically proper. This is a limiting process. So the limit as, I haven't used n yet, so I'll use n. As n goes to infinity of 2 natural log of the natural log of x. And then I've got n to 2 down here. So I'm back into limits. This is that infinity process that you might not have remembered very well. Oh man, I should have really used not n. So I've got, oh goodness, 2 natural log of the natural log of n, because there weren't enough n's already, minus 2 natural log of the natural log of 2. Okay, I'm not going to worry about simplifying this except to say it's a number. Do you agree?
Yes.
It's a number. Yeah, so this is a constant, this is a number. What's going on with this as n goes to infinity? Well, what does happen to a natural log as the log inputs go to infinity? They increase. And without bound, right? They continue to increase, albeit very slowly, forever. This is the graph I just drew before. So the inputs are increasing, and we're going to do it twice because it's the natural log of the natural log, right? So inputs going to infinity, and then I'm going to take those values that are going to infinity, I'm going to do them into the log again, and they're going to go to infinity. Everything's going to infinity. So this whole expression is actually infinite. Agreed? Now, I've got infinity minus a constant. Obviously, that's not actual value. And even if it were to give me a value here, I wouldn't be able to say that it converged to that value, right? But this is actually going to infinity. So this will diverge. And because the integration diverges, so also the series will diverge. The sum of the series will diverge. Okay, I promised to show you, and at least I'll get to this part today, an example of what we had all hoped would not happen before last section, because it would be so nice to see the limit going to 0 of the sequence and to say then that means the series converges. It would be beautiful and be wonderful. Unfortunately, we're about to burst the bubble. This is called the harmonic series. It does not create harmony. That's not what it does. All right, so we're going to consider a very specific sequence and take its summation. So the series we're going to be looking at is k equal 1 to infinity of 1 over k. First thing I want you to note, what is the limit of this sequence?
0.
It is 0. The limit is 0, okay? So we might be inclined to think, hope, or pray, I'm not sure, but to believe anyway, that the sum converges. We would be inclined to believe that. The limit's going to 0. It's a good first start, right? It's a good first sort of check-off start. I think it might go to 0, or it goes to 0, so I think it might converge. So let's look further. So this summation from k equal 1 to infinity of 1 over k is 1 over 1 plus 1 over 2 plus 1 over 3 like this, right? And S sub n corresponds to the first, I'm sorry, I should say to the sum of the first. In terms. So I'm going to draw us a picture of the function that this is. I'm not going to do it with that. Get a little thinner and that'll work. Of the function that this is actually picturing, hopefully, in our mind. So if you looked at 1 over 1, actually I'll just make it kind of enlarged. Let's say that this value right here is 1. Then you have this point. And then you had at x equals 2, you have 1/2. And when x is equal to 3 or k is equal to 3, you have 1/3. And when k is equal to 4, you have 1/4. And these are distinct points, right? This is not continuous, actually. These curves that we're looking at have discrete inputs, okay? Because they're sequences, they're not actually functions that we're talking about with continuous inputs. So S sub n corresponds to the sum of the first n terms. I'll say it this way, which is the area of the first n rectangles. Let me fix my picture so you can see them. So I'm going to sketch in the curve that we're talking about because I'm going to reference it here in a minute. And we are talking about the rectangles that are the leftmost rectangles, like this. So this would represent S sub n for 3, so S sub 3, the first 3 rectangles. There, I'm at the end of that line. And each rectangle lies above y equal 1 over x. So, S sub n is actually greater than or equal to the area under the curve. The area of the curve, another name for that would be equal to 1 to n plus 1, 1 over x dx. And we just did a integration much like this, and you guys remembered that this was the natural log of x, which would be, I'll put it in there, evaluated at n plus 1. So the natural log of n plus 1 minus the natural log of 1, which is 0. The natural log of n plus 1, but the limit as n goes to infinity of the natural log of n plus 1 is infinite. So S sub n is actually greater than or equal to infinity. Hence, the summation from k equal 1 to infinity of 1 over k diverges. Even though the limit was 0. Earth has been shattered, right? Your whole world has come crashing to a halt. This did not work out like we wanted it to. And you might find yourself saying, okay, well, if there's one of these guys, 1 over k that doesn't work, are there more? And the answer is actually yes. But there's a way to determine it without testing every single one. That's the good news of the day. We don't have to test every single one of them to decide, how about this one? Does this one work, or is this one not working? And that's actually theorem 911. Theorem 9.11 says the following. This is called the pSeries, by the way. The summation from n equal 1 to infinity of 1 over n to the p converges for all p greater than 1 and diverges when p is between 0 and 1. So my harmonic series, if I'm thinking about it from this perspective, is exactly the case when that p-value equals 1, right? And if that p-value, that exponent on the n in the denominator, is anything smaller than 1, 0.9, it's also going to diverge. But if it's bigger than 1, 1.1, it will converge. And let me just show you how we use it real quick, and then this actually is the last thing in this section. That was supposed to be an E, for example. Confirm the convergence or divergence. So the summation starting point is irrelevant. This one happens to start at 6. This is 4 over k to the 1/2. Will this converge or diverge?
Diverge.
It will diverge. So how do we write that down? Well, it diverges by the pSeries test. Why?
Because the exponent is in between 0 and 1.
Because p is less than, yeah, I'll say it the way you did. That's better. P is between 0 and 1. Or if you want to write this down, you can say because 1/2 is between 0 and 1. I shouldn't have put the equals there. Looks like that. That's why. And that's exactly how simple the pSeries test is to use. It's a comparison to the number 1. All right, I will get the web assign posted for this later this afternoon, this evening. This is page 609, number 2, 5, 16, 19, 30, 34, and 37. A bit shorter than the last one. The good news is that it's over a long weekend. The bad news is that it's over the weekend at all. So we have two assignments now that are due, 9.2 and 9.3, both due Wednesday, both the written and the online. All right?